Welcome back. Now that we've taken care of the nuts and bolts of differential calculus, in this module we're going to go back and take a look at some of the more sophisticated things we can tackle, but also at some of the more realistic problems that we can tackle. So, whereas admittedly some of the examples that you have seen in the previous presentations very well were just practice examples, in this module we're going to look at stuff that you really will see in courses like statistics for this presentation or physics for the optimization presentation. So let's get to it. The subject for this presentation is the graphing of parameter-dependent families of functions, and the main thing that we're going to look at as an example are normal distributions, which are very important for statistics. So, as you are also accustomed to in my presentations, I always try to answer the question as to why we need those things, and you've already seen my standard intro into why we need parameters probably several times, and it may be a little bit long-winded, I admit that, but basically in my experience working with parameters is uncomfortable, and if that was also uncomfortable for you, that's nothing to be self-conscious about, because after all, working with parameters is most likely something you've never done before, and that means an adjustment needs to be made. And on the other hand, remember from brain research, you have only so many spaces in your memory that you can use to keep track of things, and when you throw parameters in there, all of a sudden these spaces can be sucked up by the parameters. So yes, this is definitely an added layer of difficulty. And yet, parameters can help. In the soda can design example, we've carried letters instead of all those ugly 4-place decimals through the computation, and that made things a little bit easier to read, at least after you're used to carrying letters rather than all those decimals. And I mean, those decimals, they were ugly. There's nothing else I can say about that. That's not a value judgment on the design. The design is good, but carrying 4-place decimals just isn't necessarily my cup of tea. For this presentation, we're looking at functions that sometimes arise as families that depend on a parameter, and that happens, for example, in statistics with normal distributions, as well as all sorts of other distributions. And in those situations, we want to know the properties of the whole family. We don't want to just graph one function, because it may well be that the behavior of the family changes as the parameter changes. But that means that we must analyze the parameter-dependent expressions that defines a family as a whole. We can't just look at examples. And, well, our one and only example here is a family of functions from statistics, which is the family of functions f of x equals 1 over root 2 pi sigma. The sigma is not underneath the root. E to the negative x minus mu quantity squared over 2 sigma squared. That's called the family of normal distribution functions. It has two parameters, mu and sigma, and we're going to go about analyzing this family as if you've never seen this family before, and as if you don't know the name, which I'll disclose at the end. And that's because when you are given a new parameter-dependent family of functions, that's your situation. With a little bit of pattern recognition, we may be able to recognize certain features already from the expression. For example, the mu only occurs in the x minus mu, so the mu will be some kind of a horizontal shift. So depending on what mu is, we have a certain shape, and the mu just shifts that left to right and vice versa. And the sigma apparently has something to do with how tall the thing is, because small sigmas will make this factor out front here rather large. But other than that, the effect of the 2 sigma squared in the denominator of the exponent, that's not necessarily something that I can see right away. And the e to negative something squared, that's another thing that would take a little bit to guess the shape of. It can be done, certainly, especially with some experience, but to be quite honest, I don't recall when I saw this family of functions first, and I don't recall if I was able to recognize the shape from the expression, or if I can just now recognize the shape from the expression because I've seen it often enough. And so when that is the case, a discussion of the shape of the function with the methods of calculus with graphing methods is exactly what can disclose all the features of the function. This family of functions plays a central role in statistics, and so what we want to do is we want to sketch its graph. How do we do that? Well, standard approach, growth behavior, concavity, asymptotes, and all that other good stuff. So let's take a look at that. The growth behavior, we need to find the first derivative. We need to find the first derivative with respect to x, right? Remember when we work with parameters, the parameters act like constants. The parameters are constants, so we're only worrying about x here. That means the 1 over root 2 pi times sigma, that's just a constant, that stays out front. And then we have to take the derivative of an exponential. We know how to do that. The exponential comes back and we take the derivative of the exponent. So we get e to the negative x minus mu squared over 2 sigma squared. And then we have the derivative of the exponent. Let's see, the negative sign stays with us. The division by 2 sigma squared stays with us because those are constants. The derivative of x minus mu squared is 2x minus mu times 1. So it should be just negative 2x minus mu over 2 sigma squared. That's good. And well, now the 2's, of course, cancel. And then we can collect terms a little bit. So the negative here with the subtraction turns the x minus mu into a mu minus x. The 2's have cancelled, and the sigma in the denominator becomes a sigma cubed. And that's already it in terms of simplifying the derivative. We set that equal to 0, and we realize because the exponential is never 0 and everything else are constants, that we just get that x equals mu is the one place where this derivative is equal to 0. And that means we can start our usual discussion of the growth behavior. There is one point where the growth behavior potentially can change, one critical point, and that's mu. And we need a checkpoint to the left and to the right of mu. And well, because we don't know what mu is, and because we don't know really what to add in or subtract, we go with something that actually scales like the function itself. I'm going to use mu minus sigma and mu plus sigma in that fashion. I can get some kinds of cancellations here. It turns out the cancellations aren't that critical after all, but it makes things a little bit easier to read. So let's see, f prime at mu minus sigma. You know how that goes by now if you are trying to do that in your head, and that is that you want to dismiss certain terms. And here we really have no choice but to do it in our heads, because these things are all given just symbolically, right? So let's first realize that the exponential, which of course is rather ugly, but the exponential is always positive, and so we don't have to worry about it for the sign discussion. Similarly, the denominator here, and my machine doesn't necessarily select in a pretty fashion, but the denominator here, that's also always positive. One thing that I should have said is sigma is always supposed to be a positive real number. That is one of the properties of this family. It is not considered for negative sigmas. And so that means this denominator is also always positive. And mu minus sigma, well, that is plus sigma, and that will be positive then. And similarly, when I plug in x equals mu plus sigma, everything except mu minus x is positive. And mu minus quantity mu plus sigma is negative sigma, which is negative. Okay, so that means our function is first increasing and then decreasing, and that's already it for the growth behavior. Now you've seen here that as we're working with this parameter, again, we're trying to chunk the function into certain parts that we can handle at once, so that we don't have to contend with this not seeing the forest for the trees phenomenon. And other than that, we just have to pretty much analyze every little chunk separately. Okay, for concavity, well, we need to get the second derivative, and that means we need to take the derivative of the first derivative. And the second derivative here now, let's see, how does that go? The denominator is constant, so that one we can probably just pull out or just copy down. And then the function is a product this time around. It's the product of mu minus x times this exponential. So by the product rule, we first take the derivative of the first times the second. Okay, so yeah, we pulled out a negative 1 over root 2 pi sigma cubed. That's the derivative of the first term, right? Because the derivative of mu minus x over root 2 pi sigma cubed with respect to x is just -1 over root 2 pi sigma cubed times the second, plus the second, plus the first term times the derivative of the second term, which was the exponential times the derivative of the exponent, which was 2x minus mu over 2 sigma squared. And now we can see once more the 2's cancel. The sigma squared here, together with the sigma cubed, becomes a sigma to the fifth. The minus x minus mu is a mu minus x, so we end up with a mu minus x quantity squared, and that should be it on that side of the equation. Right, and so basically I'm already anticipating that I need a sigma to the fifth as a denominator, so I expanded the first term here with sigma squared. Everything else stayed the same in the first term. In the second term we just get a mu minus x quantity squared, the root 2 pi sigma to the fifth, the 2's cancel, and the exponential stayed here. And now we know that the 1 over root 2 pi sigma to the fifth times the exponential, that factors out. Or, well, we just find a common, we've got the common denominator here. Everything is the same except the x minus mu squared, which is the same as mu minus x squared, and the minus sigma squared. And so essentially what I've done is here I've factored out the denominator root 2 pi sigma to the fifth and the exponential, and then just put what remains in the numerator here. Same thing as before, we have to set things equal to 0. When we do that, we get x minus mu quantity squared being sigma squared. That gives us that x is mu plus minus sigma, because when we take the square root, remember, square root of sigma squared, because sigma is supposed to be positive, we end up with just sigma absolute value, which is sigma, and plus minus from solving equation. Then we bring the mu over, so x is mu plus minus sigma. Our two possible inflection points are therefore then marked on a number line. We get mu minus sigma and mu plus sigma. We need 3 checkpoints, and those 3 checkpoints I made mu minus 2 sigma, and mu plus 2 sigma. This time around, I really have to scale this in terms of sigma, because, well, if I want to be to the left of mu minus sigma, mu minus 2 sigma looks as good as can be here. Okay, so now we have to test the signs, and again, same discussion as before. If we're looking at that second derivative, the exponential is always positive, which is wonderful. We don't have to worry about it. The denominator is always positive because sigma is positive, so we don't have to worry about it. So we really only have to contend with the numerator, which is probably bad enough, but let's see. Plugging in mu minus 2 sigma gives us mu minus 2 sigma minus mu, which is just -2 sigma quantity squared. That gives us 4 sigma squared, and 4 sigma squared minus sigma squared is positive. So the function, the second derivative is positive here. When we plug in mu, we get mu minus mu, which is 0 minus sigma squared. That's negative, so we get a negative here. And mu plus 2 sigma minus mu, that gives us 2 sigma. If we square that, we get 4 sigma squared minus sigma squared. That gives us a positive return again, and so f double prime is positive here, which means the function is concave up, concave down, and concave up. The y-intercept actually is not useful here, and that is because with us not knowing what mu is, and with us anticipating that mu just shifts the function back and forth, we really don't know where the y-axis will be with respect to what arguably will be the center of the shape, so we really aren't going to worry about the y-intercept. The x-intercepts, well, there aren't any because exponentials are never 0. Vertical asymptotes, well, exponentials don't have vertical asymptotes. The horizontal asymptote is y equals 0, and that is because when x gets large, you get e to the negative square of a really large number, and we know e to a negative exponent goes to 0 as that negative exponent gets large and negative, and that works for x going to plus infinity as well as for x going to minus infinity, because after all, x minus mu is being squared, so any kinds of signs of x are being erased. Okay, then we have vertical tangents. Well, we don't have vertical tangents here, and so we want to plot at least some points, and the interesting points are certainly where we have our maximum and where we have our inflection points. So we need f of mu, which is, well, when you plug in mu, your exponent becomes 0 e to the 0th is 1, so f of mu is just 1 over root 2 pi sigma. And then we have f of mu plus minus sigma. Again, the stuff out front stays the same. And mu plus minus sigma minus mu is just plus minus sigma squared. And the square, of course, erases the negative signs, so we get just sigma squared, and sigma squared over sigma squared is 1, and so the exponential is just e to the negative 1/2 there. Those are the points that we can plot. And basically, what we know there is then that the value 1 over root 2 pi sigma is times e to the negative 1/2 is smaller than the 1 over root 2 pi sigma by exactly the scaling e to the negative 1/2, but that's about it. Summary, well, what do we have? We have 3 places where the behavior changes, and those are mu minus sigma, mu, and mu plus sigma, which means we get 3 vertical lines that cut everything up into 4 different regions. Within those regions, the function is increasing concave up, then increasing concave down, then decreasing concave down, and then decreasing concave up. And so we can draw a number line now. We won't get a y-axis because we don't know where 0 is, but we know where mu minus sigma, mu, and mu plus sigma are. And well, now we have to graph the function, and we realize the horizontal asymptote is 0, so the function will come out rather flat over here and then be increasing concave up. Well, okay, first we plot the points. And as I said, the points for mu minus sigma and mu plus sigma are lower than the center point, and I think I did that to scale, so this is really a percentage e to the negative 1/2 of this height here. And now the function comes in from the left, being increasing and concave up, and it has to be very flat over here because this is a horizontal asymptote. So here's where the function comes in. Then the function changes to increasing concave down, and because we've got a target point, it's now pretty easy to draw that in. Then the same thing happens on the other side, because we could argue here, even though the function is neither even nor odd, it is symmetric with respect to mu, because whether you step a certain distance to the right of mu or a certain distance to the left of mu, the square erases that and you'll get the same value. So the function will be decreasing concave down and with the same shape as to the left coming down here. And then it'll be decreasing concave up, going towards its horizontal asymptote as x goes to plus infinity. And that's the shape. And here's where we can see now what the shape is. The shape is a bell curve, and normal distributions are also called the bell curve. And then certainly, once you know that name, then you can go back and look at this shape and see, yeah, clearly the mu is the center of the bell, and the sigma has something to do with the height and the width. The nice thing certainly is that here we have mentally / symbolically created and predicted that shape, and so when we're now seeing these animations, and there's nothing wrong with looking at animations of these things in order to get a better visualization, we can say that yes, this animation is consistent with what we have figured out, and in some ways we already can see the animation in our minds. We remember that mu just is basically what shifts the whole distribution from left to right, and that's exactly what is happening here. As the parameter mu varies, the shape stays the same. I kept the sigma at 1, and other than that, the whole shape just translates left to right as mu increases, which is something that we knew from our discussion. And similarly, the effect of sigma was, well, sigma is where those inflection points are located, and so if sigma is small, they're close together, which means that the bell is very narrow and tall, because we're dividing by sigma here, which gives us a tall shape in the middle. Whereas when sigma gets large, this thing gets flatter, but because the inflection points move farther apart, it also gets wider, and that's what this animation shows here, that as sigma increases, this thing gets flatter and wider. It keeps spreading out. And well, that's already it. So remember, the nice thing here about this admittedly hard work that we had to do with those symbols is that we have better mental ownership of what this shape looks like, because we didn't just watch these animations, because as nice as they are, if we just watch them, it's just a glorified way of watching TV, but we were able to mentally predict what these animations would do. And that's a whole different level of connection to the material than otherwise. So in some ways, I would hope that if/when you are taking statistics, you will be able to predict these shapes a little bit better, and you may even have to do this with more complicated distributions, and hopefully this will have prepared you for that. Thank you very much.